So now we're ready to go and make our internal pictures now that we know all of our external, all of our reactions, I'll call them. I'll start next. We need both D and E just to the left of the 10 kilonewton load. Let's start with E. I'm going to call it E minus because it's just to the left of where point E is located. So take a minute and draw. Well, actually, let's talk about first, if we're cutting at point E or just to the left of point E, what the options are for the picture we could draw. So cutting through point E just to the left of this 10 kilonewton load, what would one option for the segment that we draw for our free body diagram be? Yeah.
Everything to the right.
Right, everything to the right of that cut, including the 10 kilonewton load acting on point E. I would say this is probably our easiest, our best option because the least amount of stuff is going on to the right of it. One other option would be we take everything to the right of it, so encompassing this entire structure to the left, everything to the left of it, this entire structure with the distributed load. But because this is a frames and machine type of problem, we actually have another option. We don't have to take everything to the left. We can take everything to the left up to point B. Basically, if we take this picture and we know what's happening at point B, so we could kind of truncate it there and then include the BX and the BY in that picture. That would be a third option for a way to model this segment. If it's not a frames and machines type of problem, we can't just split it in the middle because that would expose another internal load. But because we know what this external connection is, that would be another way to model it. Again, I would suggest taking everything to the right. I think is going to be an easier way to do this one. All three, though, will give you the same answer. Coming out of E, we'll have P sub E, V sub E down, and M sub E, I'll assume, is clockwise. So using the free body diagram at E, or E minus in this case, what are the internal forces we find, at least based on the assumptions that I made, or if you made different ones, that's okay. What do you get for the internal normal force at E? Right. In this case, we get 0. It's the only force in the x direction, so it's not in tension or compression. The internal shear force. Right. According to VE down, you get a -5 kilonewtons. And the internal bending moment at point E, 7.5 kilonewton meters positive. Those are the three internal forces acting at E, or just to the left of E, so we're including that 10 kilonewton load in this picture. If we took the other side of the cut, that would not have it. But if you want for extra practice to draw that side, you will get these same answers if you make equal and opposite direction assumptions also. Finally, we want to know the internal loads at point D. We have, again, a couple of options. If we make that transverse slice through D, we can take everything to the left. So we'll have a distributed load. We'll have what's happening at the wall acting on that segment. We could take the cut and take everything to the right. Or we could take the cut and take everything to the right up to and including B. Again, referring back to this picture, we include the BX and the BY as modeled in this picture because we're only considering this beam. We're not considering what's happening on this beam. Just like in point E, I think it's probably easiest to take everything to the left rather than dealing with the larger amount or dealing with the pin connection. So I will choose in this one to take everything to the left of D. I think it's a little bit simpler. I have a wall reaction at A. which I found was 11 kilonewtons up, and 24 kilonewton meters of moment in the counterclockwise direction. AX was 0. And I have the distributed load that acts from A to D. In that case, it's an intensity of 2 kilonewtons per meter. This has a total length of 1.5 meters. So the equivalent point load that I can draw here will be 3 kilonewtons acting at the center of this segment of beam. At the surface of the cut, I'll have P sub D coming out of it. I'll assume V sub D up, and I'll assume M sub D clockwise. Counterclockwise in this one. All right, so in this last step, what do we get for the internal normal force at D? All right, also 0 here, still no other forces in the x direction. Our internal shear force at point D, right, we should get negative 8 kilonewtons. And our internal moment, yes, negative 9.75 kilonewton meters. So we see between point D and at least just the left of E, normal force is the same. There is a change in the internal shear force, and there's a change in sign and magnitude of the internal bending moment.